Hi ladies, this is Mrs. Blaufuss here, and today we're going to talk about visual reasoning. This is lesson 2.1 in your textbook, and today we have a new term Venn diagram, and we'll demonstrate what those look like a little later in the lesson. Something that you may have seen before, so we'll just review the layout and how to read those. But first I want you to refresh some of the formulas that you know, formulas for area. So there are 3 formulas for area that we use pretty often, and those are area of a circle, area of a triangle, and area of a rectangle. Now, these are in your student handbook on page 51. This is in 2019. So the 2019-2020 handbook is on 51 has your area formulas. So let's just refresh our area formulas. And if you remember what area describes, it describes the space inside of a figure. Okay, so for a circle, area equals pi times the radius squared. And remember that the radius measures the center of the circle to any point on the outside of the circle. So these are all radii, and they are all congruent lengths. In a triangle, we have a formula for area, and that is 1/2 base times height. Okay, so here's the base of our triangle, and the height is the distance that's perpendicular from the base to the top. So that's our height. And then the third one we're going to talk about today is the area of a rectangle. So here's your rectangle, and we describe area of a rectangle as length times width. Doesn't really matter which one you call length and which one you call width, but you will take the product of the length and the width. And then the last term I want to refresh in your memories is perimeter. Perimeter describes the distance around a figure. So I always think of perimeter as fencing. So how much fencing would I need to go around the outside of this rectangle? So in a rectangle, I'm going to add the length plus the width plus the length plus the width. Okay, so my perimeter is going to be length plus width plus length plus width, or, and you may remember this formula, 2L plus 2W. And then lastly, in a circle, we have a perimeter, but in a circle, we call it circumference. And we say that the circumference is equal to 2 pi times the radius, or we can say the circumference is equal to pi times the diameter, where the diameter goes all the way across the circle and through the center. So this should be review for you. You should have seen this before, but for some of you, it might have been a while since you've seen this last. So that's why I just want to make sure that you review those formulas. So please put those formulas on your flashcards or wherever you put your vocabulary, because you'll use this throughout the semester. So I want you guys to look at your note sheet, and this problem is on your note sheet. And I want you to take a minute and think about it, draw a picture on your note sheet, and then come to a conclusion on how far the bookworm is going to travel. So I'll give you a minute to read through the problem and to draw your picture, and you can pause the video while you work. So you should have already drawn a picture, and some of you maybe already solved the problem, but now let's think a little bit more in detail about our pictures. So it says that we have volume 1 and volume 2 math books sitting next to each other on a shelf. So let me just sketch that out. Here's a math book, And here's another math book. Okay, they're next to each other on a shelf. This can be volume 1, this can be volume 2. Volume 1 is on the left and volume 2 is on the right, so they're in order. And it says each front and back cover is 1/8 inch thick. So I'm going to go ahead and on my picture, I'm going to sketch in those covers. Okay, and I'm just going to label them each as 1/8 so that I can visualize the space that's being taken up. And then it says the pages portion of the book is each 1 inch thick. Okay, so each of these pages portion is 1 inch thick. So if you just read through the problem and you solved it right away, you probably added everything together and you went from here all the way to here, right? And you would have gotten 2 2/8 or 2 1/4. But now I want you to think about how these books are laid out. And this is the power of visual reasoning. So if you can label the first page and the last page of each book, then you'll be able to more accurately visualize your picture. Okay, so let's look at this first book. If I pull this book off the shelf and I open it up, this is actually the front cover, right? That means right here is page 1. Okay, same for my second book. This is page 1. So then that means that this is actually the last page. And therefore, this is actually the last page of my book. Okay, so now with my diagram being labeled, I can visualize where the bookworm actually travels. So he starts here at the first page of the first book and chews all the way to the last page of the second book. So actually, he only goes through the front binding of the first book and the back binding of the second book. So he only travels 2/8 or 1/4 of an inch. Okay, let's look at another example. In this example, it says Harold and Dinah and Linda are standing on a flat, dry field reading their treasure map. This flat field, we can visualize that as a plane. Harold is standing at one of the features marked on the map, a gnarled tree stump, and Dinah is standing atop a large block boulder. The map shows that the treasure is buried 60 meters from the tree stump. That's where Harold is standing. And 40 meters from the black boulder, which is where Dinah is standing. Harold and Dinah are standing 80 meters apart. What is the locus of the points where the treasure might be hiding? So the locus, just to define this term, locus means any point that satisfies the conditions. Or points that satisfy the given conditions. Satisfy. Okay, so I'm going to start just by sketching. We don't really care where Linda is. She's not really in the story. So we're just going to ignore her. It says that Harold and Dinah are standing 80 meters apart. Okay, let's start there. Then it says that the treasure is buried 60 meters from Harold and 40 meters from Dinah. So let's visualize all of the possible points that could be 40 meters away or 60 meters away from Harold. Okay, so I'm just going to take this line and I'm going to make it, here's 80 meters, so about this long. Now, if I rotate this all the way around and I keep it at 60 meters, all of these points are the same distance away from Harold. They are all 60 meters away from Harold. Okay, so I need something that's going to represent all of those points. And so I can do that by drawing a circle. Okay, so here are all of the points that are 60 meters away from Harold. And I'll just sketch in that this is 60 meters. Now I want to do the same kind of thing, and I want to visualize all of the possible points that are 40 meters away from Dina. So I'm going to do the same thing. Here's 40 meters. Okay, so I'm going to take this and I'm going to visualize all of these points that are 40 meters away. Okay, so these are every single point where this orange line touches is going to be 40 meters away. So I'm going to do the same thing. I'm going to draw a circle, and I'm going to make the radius, instead of 60 meters, I'm going to make it 40 meters. So now on the orange line, I can see everything that's 40 meters away from Dina, and everything that's 60 meters away from Harold is shown on the black line. So here are two possible locus points where the treasure might be buried. Now, in this class, we're going to get into circles a little later in the year, but you've already been introduced to the radius in former math classes. So take what you already know and take what you can already visualize and apply it to what we're doing here. So remember, in geometry, it's a little bit different than your other math classes, but we need all of those things that you've learned up until this point. We need those in order to solve these kind of geometric problems. Okay, so on your note sheet, you see a third example, and I want you to try this one on your own. So pause the video while you work, and when you have a solution, you can unpause, and I'll go through the solution. All right, we're going to start by drawing a picture, and in this example, we're looking to build a fence. So remember, when you're building a fence, that's perimeter. Okay, you're looking for the distance around this rectangle. So I could draw this picture and I could look at all of the points I'm going to build a fence, right? So on this first one, here we've got 5, 10, 15, 20, 25, 30, 35, 40, 45. They're not perfectly spaced, but there you go. You can see all of the fence posts I'm going to make. And then we've got a point here. So then to get 25, I got 5, 10, 15, 20, 25, and then so on. And 5, 10, 15, 20, and 25 is already there. Okay, so in an example like this, if you're going to sketch these out, you have to make sure not to count any post twice. But if you solve it using what you already know about perimeter, where perimeter is 2 times the length plus 2 times the width, so 2 times 45 plus 2 times 25. So then when you actually solve for perimeter, you get 90 plus 30, which 90 plus 50, sorry, which is 140. Now you're going to set the posts 5 feet apart. So if your total perimeter is 140, so that's the distance all the way around here, and you're going every 5 feet, you need to divide 140 by 5. And when you do that, you get 28 posts. Okay, let's look at the next piece of your note sheet, so you'll have to turn it over. And this describes Venn diagrams. Now, so far we haven't gotten into all of these specifics, but you've seen quadrilaterals and parallelograms before, and you've seen polygons before. So we're not going to get into too much detail about the specifics of the shapes right now. We will in Unit 2. But the idea here is to visualize groups of things or people or qualities. And in this case, we're looking at polygons. So in polygons, we have a bunch of different shapes. We have shapes that have 3 sides, 4 sides, 5 sides, etc. And one of those shapes is triangles. Triangles have 3 sides. Now, within triangles, we have 3 separate groups. Okay, they are all polygons, but each triangle falls into a separate group. So if we have an acute triangle, we do not also have a right triangle. Okay, so there's no overlap between these two. A triangle is either acute, it's a right triangle, or it's obtuse. Okay, it will not be all 3 of those, or even 2 of those. It will only be one. Now, you've heard before that squares are rectangles, but rectangles are not squares. So in this shape, we can see that squares are part of a bigger group. Okay, and that bigger group is rectangles. And we can keep expanding on those groups getting larger and larger. So squares are rectangles, but rectangles are not squares. Squares are also parallelograms, which is a 4-sided figure, has 2 parallel sides. Squares hold those qualities, but parallelograms are not squares. Okay, so that's how we're reading the Venn diagrams. We can represent our diagrams using ovals, and each oval represents a specific group of things, and ovals inside larger ovals mean that, in this case, the small oval is part of the larger oval. Okay, so let's look at, here we go. Let's look at creating a Venn diagram relating DSHA high school students, freshmen, sophomores, juniors, seniors, and geometry students. Okay, so let's start just by, here's all of our DSHA students. Okay, all of these things, freshmen, sophomores, juniors, and geometry students at DSHA, all of these groups of people are part of DSHA. Now, we know that freshmen are just freshmen. They're not sophomores, they're not juniors, they're not seniors. Freshmen are freshmen. So they get their own circle. And we'll label it freshmen. Sophomores are sophomores. They're not juniors, they're not seniors, they're not freshmen. So they get their own circle. These are sophomores. And then same is true with juniors and seniors. They get their own oval. Here's our junior oval. And lastly, our senior oval. And let's see, purple. Okay. So we know that freshmen, sophomores, juniors, and seniors, they're all part of separate groups. But geometry students, they include more than just one grade. So in geometry, we have some sophomores, some juniors, and some seniors. To move my oval around a little bit, but some sophomores, some juniors, and some seniors. So not all sophomores take geometry, but some do. Not all juniors take geometry, but some do, and not all seniors take geometry, but some do. And none of our freshmen are in geometry this year. So now let's practice reading our Venn diagram. So in this diagram, we have 5 students who work just after school. Okay, they're only in the after school group. We have 17 who work just weekends, and we have 3 that work weekends and after school. So how many students work after school and on weekends? Okay, that's where this overlaps. The after school and weekend circle overlaps, and that's 3 students. Now, how many students total, let's think of how many students total work after school. We've got 5 that work just after school and 3 that do both. Okay, so that's 8 students total that work after school. And working weekends, we have 17 that just work weekends and 3 that do both. So that's 20 total that work weekends. So how many students work after school or on weekends? So how many students work total? That's 28. 8 that work after school, 20 that work on the weekends, 8 that work after school or on the weekends. So that's our lesson in visualizing our reasoning and drawing our diagrams. So please jot down any questions that you have and bring them to class with you the next time I see you. Thank you.